line here so that we can think about them in one dimension. And theta s is the source angle. So if we have some axis here that we're going to allow to go through the center of some lens, theta is the angle on the sky between the source back here and the lens up here that you would see if there were no such thing as gravitational lensing. Okay. And then theta I is where you actually see the object after there is lensing, because this ray, the direct ray, of course, doesn't happen. The ray that reaches your eyeball over here is the one that heads off this way and then gets bent by this alpha hat and then comes to your eyes. So this larger angle, theta I, is where you actually see. And the I is for image, okay? So in lensing lingo, the I and the S are for image and source planes all the time. Now, we can figure out the relation between the actual bend angle and the apparent one. The apparent deflection angle we'll get to in a second, but let's see, there's a relation that we can build here, which is that the distance from this point here to this point down here, we can come up with two ways. It's either theta I times the distance from the observer to the source by this triangle, right? But it also can be expressed as the sum of this distance, which is theta s times, again, the distance from observer to source, plus alpha hat times the distance from the source true position to its apparent position, right? So this equation here, theta I times DOS equals theta S times DOS plus alpha hat times DLS, comes from that geometry. Does that make sense? Give me a nod, okay. All right, so we can solve that equation for theta S, the source, as a function of the image position, and it's just theta I minus alpha hat times DLS over DOS, right? And if this is a point source of mass and we use this equation right here, we get this for the relation between the source position and the image position. And notice that the image position appears twice here, right? It appears in determining what the bend angle was and also in its original. Okay, so this is the basic point mass gravitational lensing formula. Okay. And this thing over here is what we would call the apparent deflection, right? So alpha hat times DLS over DOS is how far it looks like the thing moves, which is not the same as the angle that the photon was actually bent. All right, so that's where we start, and then we're just going to make this more complicated all the time. There is one caveat I want to throw at you, which is that these are the proper angular diameter distances. And in general relativity, it is not true that this distance plus this distance equals this distance. Okay. In a flat universe, that is true for the co-moving distances, but it's not true for the in a non-flat universe, and it's also not true for these proper angular diameter distances. There are extra factors of 1 plus c that show up. Okay. All right. So let's think a little bit more generally about circularly symmetric lenses, not just a point mass, but any mass that is a function of radius on the sky. And you may recall from your mechanics class that Einstein proved, not Einstein, Newton, even better, proved that a spherical shell of mass acts as a point mass on anything that's outside the shell, right? And has no gravitational effect on anything inside the shell. Well, the same thing is true for a 2D ring of mass on the sky. If a ray passes outside of it, right, the bend angle is just like it was a point mass. And if the ray passes inside of it, it's not deflected at all, right? So we can take our equation for a point mass and generalize it. Instead of just having the mass, what we have is the mass that's interior to wherever the ray passed by the lens. Okay, that's what this symbol m less than theta I is. That's the mass interior to some angle from the center. And this whole thing here is what we would call alpha, the apparent bend angle, again, a function of I. Now, if we're looking at a source and we want to figure out where the image will appear, okay, We can do that graphically with this helpful diagram here. On the x-axis is angle, theta I, and on the y-axis is this scaled bend angle, right? The apparent deflection. And this formula here, which looks like 1 over theta I, for instance, if m is constant, we would write as this hyperbola, alpha of theta I. And of course, it bends the other way if it's on the other side of the mass. And then this green line here is the equation for theta s equals theta I minus alpha if the source is actually located right here at theta s. Now, images are going to appear, that is, this equation is solved when the green line and the black line cross. Okay. So we can see in this case that we would get one image here and one image on this side. There's something special that happens if the source is right in the middle. Okay. That is, the source is directly behind the lens. All right. And if we have a solution such that an image will appear, let's see, if theta s equals 0, then there'll be perhaps, if we're lucky, some point where the angle and the bend angle are the same. And what that means is we get an Einstein ring. Okay. So maybe it's best if I try to draw this. See if I can get this to work. Document camera. Maybe I can't get it to work. I have to turn it on or something. That'll help. There we go. Okay. And I'm going to zoom out a little bit. All right. So if you're here observing, and here's your lens, and there we go. And that's your source, all right? If there is an angle here, theta I, and I'm going to call it theta E for Einstein ring, where a ray can do that, then a ray can also do this by the symmetry around this line, and actually any point on the sky in a ring around there. That's not going to work for them because it's actually sharing from my screen. So the Zoom people are going to have trouble with this.
Sorry.
Yeah. So anyway, when you look at this thing, what you're going to see is a ring of light surrounding the lens, right? All of which goes back. And Einstein hypothesized that this could happen back, I don't know, in 1920s maybe. But he said, oh, it'd be so rare that you would never see this, right? And one of the problems is that Einstein didn't really know about the existence of galaxies. And it turns out that it's rarer for stars, but if galaxies or clusters of galaxies are lenses, it can happen quite relatively frequently. Okay, and there's a picture of one of them. Okay, I'm gonna my mic. Okay, and let's see, how do I get back here? There we go. Okay, so let's get the right projector back to my laptop, left projector back to the PC. There we go. Okay. So Einstein rings can happen, and we can solve our equations. For the Einstein ring to happen, the deflection angle has to equal the apparent angle, or the source angle, image angle. And we can write that condition is solved at the Einstein radius, theta E. And so we can solve this equation, and there it is, right? So that's the equation for the Einstein ring radius of a point mass. So at this point, I want to switch over to the other screen and have us do a little bit of work as we go along here. And has everybody been able to access some version of this notebook? Okay, good. So first of all, if you're doing this on the Colab, you have to run this first cell to install AstroPi, which is the only special package here that, and I'm going to introduce you to some of AstroPi's very useful features if you haven't seen them before. And then there's a few galaxy catalogs and images that we're going to analyze over the course of today and tomorrow that it will download. All right. So that should work for you. And then we get into the usual thing where we import a bunch of stuff. And now problem number one. What's the gravitational deflection angle of a photon grazing the limb of the sun in arc seconds? Okay. Before we get to that, I just want to point out this really nice feature of AstroPi is that it knows a bit about cosmology and it knows about units, right? So what I've done is imported the Planck 2018 cosmological parameters solution as something called Cosmo. And that object can give you all kinds of things, for instance, the Hubble constant at any redshift. And I will ask it to convert that into units of inverse seconds. And we get 2 times 10 to the minus 18 inverse seconds, okay? So there's just an example of how to use this. And another thing that I've done for us is to answer part 1A. What's the gravitational deflection angle of a photon grazing the limb of the sun? Well, the formula for the deflection angle is just our 4gm over RC squared. And so let's just write that here, 4. And now the constants part of AstroPi units knows about G, it knows about the mass of the sun, it knows the radius of the sun, and it knows about C. So this is all we have to do, except to turn it into arc seconds. And there's the famous answer, 1.75 arc seconds. Right? So that was what was observed in the eclipse of, I think, 2018 that confirmed that general relativity was correct. Okay. All right, so now I'm going to let you all take a minute to think about something. How far away from the sun would you have to be in order to see some distant star turned into an Einstein ring that surrounds the sun? Okay. So we're too close to it. And I'll give you a hint why. It deflects things by 1.75 arc seconds, right? To us, the sun is 30 arc minutes across, right? So if the things that bend by 1.75 arc seconds on either side of the sun have not had a chance to converge by the time they reach Earth. So I'm going to give you about 5 minutes to think through how far away, how would you figure this out, okay, knowing that deflection angle. And if you can do it in AstroPi, so much the better, but you can do this with pencil and paper too. Okay. And if anybody has any questions or anything as we go along, please jump up and down or something so I could see. What are you? I'm gonna bring everybody back here and ask. I've read papers about people proposing a space mission to do this, to use the sun essentially as a telescope, a gravitational telescope that would give us a tremendously expanded view of a distant star and maybe its planets. So how many of you got a number that you think would make such a mission feasible? How many of you got a number that makes that idea seem ridiculous? Okay, so yeah, I think it's ridiculous. So there's a couple ways you can think about this. All right, one of them would be, let's see, to consider, I'll scroll down here on this one. Here's, and then we're going to show the camera. Okay, so here's our distant star sending parallel rays of light to the sun, and they're each bent by 1.75 arc seconds, our deflection angle, and we want them to converge at our eyeball, right? So basically what I need is for the angular radius of the sun, or if we look at this triangle here, right, 1.75 arc seconds, this is the radius of the sun. It's easiest for us to then solve for the distance. And that distance would then just be the radius of the sun divided by our deflection angle. And if I ask AstroPi to convert that to parsecs, I get 300 parsecs, right? So is that within the solar system? No. Is it closer than the nearest star? No. So we have to go pretty far out into the Milky Way before we could use the sun as a telescope. Yeah.
Why do you like
Let's see. Did I do it? I'm sorry, I'm not catching the question here. Sorry, this one. Well, I have to take the distance. Well, oh, you're right. You're right. I did make a big mistake. I already did this. So let's see, that's this computer. All right. Uh-oh, run anyway. Okay. Oh, I got to run the whole thing. Sorry. All right, you're right. There's a mistake. That didn't take long, did it, for me to make a mistake on my own problems? So yeah, it's probably better than I said, right?
I did. I killed it.
Another way that you could do this problem is to realize that in this situation, the angular radius of the sun as you view it has to equal its Einstein radius, ring radius.
Yeah, use the
Because what we need is for the ring to be bigger than the sun itself appears on the sky, so that the rays do not have to pass through the sun to get to us. Okay, that's done.
Yeah, I want to see what the solution is.
That's done. Okay.
Oh,
So not as bad. It is closer than the nearest star, but let's see what it is in AU. Okay, so you have to go 500 AU away.
Very good.
All right, so yeah, we're
We're
good.
good.
Yeah.
I'm sorry,
So,
I didn't hear. I for some reason can't hear over the noise.
Yay.
Okay. All right, so 500 something AU, which is well outside our solar system, but is now closer than the nearest star. So it's a pretty hefty space mission. All right, let's see if I can do better on my own problems in the future. Okay, so now that was for what we talked about, a point mass deflection. Now I want to introduce you to another kind of mass distribution, a circularly symmetric one that is used quite often in what we call strong lensing as an approximation for what galaxies look like, because it's a pretty good match to galaxies. It's not as good as the Navarro, Frank, and White profile that you've heard about earlier this week. But this, if we consider something like the Milky Way, other spiral galaxies, we know that they have what we call flat rotation curves, right? That the circular velocity of things orbiting the galaxy stay remarkably constant as a function of radius. So let's figure out what that means for gravitational lensing. Isaac Newton tells us that the acceleration of, say, the sun as it travels around the center of the Milky Way is v squared over r, and that has to equal g times the mass within our radius over r squared, right? Acceleration is force here with a mass scaled out. Oh, yes, sorry. This is better. Okay, there we go. All right, so we know that v squared over r is gm over r squared, and that tells it that the mass enclosed within a given radius has to equal v squared r over g. And if we want to know the density, right, the density distribution that would cause that, then the derivative of the enclosed mass with respect to radius has to equal 4 pi r squared times rho. So we can solve for the 3D density distribution of what is called the singular isothermal sphere, or SIS, as the circular velocity squared over 4 pi g r squared. Okay. I'm going to introduce now what we call the surface density, which is usually given capital sigma, not to be confused with the summation. And so that is the density integrated along the line of sight, right? So what's that for our SIS? Well, if we have a ray that's passing within some distance b of the center, then if we integrate the density along the line of sight from -infinity to infinity in the line of sight direction z, you can go through and plug this row into here, and it's an integral that you can do, and you get the simple equation v squared circular velocity over 4gb. And those of you who've had thought about dynamics a little bit, another way that this is often written is in terms of the velocity dispersion. If the stars in the Milky Way were moving in random orbits instead of in orbit organized circles, then they would have a velocity dispersion called sigma, which is √2 smaller than the circular velocity. Okay. So the common formula for the surface density of an SIS mass distribution is just sigma squared over 2g times the distance from the center b. Okay. Now we can go back and figure out what the deflection angle is. And remember that the deflection angle is 4g over c squared b times the mass enclosed within some distance b, right? That is the mass interior to the circle that we're passing through. And so to get that interior mass, I just integrate from radius 0 out to b, 2 pi r dr times the surface density of r. And if I do that, it turns out to be something very simple, 4 pi sigma squared over c squared. And you notice that the bend angle then has no dependence on b, on the distance from the center. So this is a magical thing about this SIS that makes it something nice to use for examples, and not too bad for a real galaxy, is that the bend angle is constant. Okay. All right. So at this point, let's look at the next problem. Let's see if you can figure out the angle that the Milky Way, if approximated by an SIS mass distribution, would bend light passing by it. And the circular velocity of the Milky Way is 220 kilometers per second, roughly. And remember that sigma is √2 smaller than that. And then if you write that as a formula, you can reuse the formula in your cell and consider what a very massive galaxy cluster could do. Something with a velocity dispersion of, say, 1,400 kilometers per second, which is a pretty massive galaxy cluster. So let's take a few minutes and see if you can do that one.
Wait,
Yep.
it's an input, yeah.
Mhm.
All right. Okay. So let me move ahead. And as you may notice here, we're doing something called strong lensing. We'll get to weak lensing later. And let's think about a more general mass distribution that has any sigma of r. And what we will see is, to get an Einstein ring, which will happen at the Einstein radius, we have to have theta s end up being 0. So we set the lensing equation here, to have theta s equals 0, and we will get this equation. And then if I move this to the other side and divide everything by theta e, I get that 1 has to equal this combination of constants times the mass enclosed within, this should be a theta e also, divided by theta squared. And I'm going to put a pi in here and a pi down here. And I'm going to change the theta e to b. And what we can see here is that this quantity, the enclosed mass divided by pi b squared, well, pi b squared is just the area of that ring, right? The enclosed area of the ring. So this quantity over here is what we would call the cumulative surface area, or the average surface density within the Einstein ring. And this combination of constants here is called the critical density. This is not to be confused with the critical 3D density for closing the universe. This is called the lensing critical density. And you can see that in order to have an Einstein ring, what has to be true is that the average density of the lens inside the ring has to be equal to this number here that depends only on distances called the critical density. Okay, so this is extraordinarily useful, right? Because it's telling you if you see an Einstein ring, it tells you how much mass is inside that ring. So if we go back to the picture of, whoops, wrong direction. If we go back to this picture, if we can measure the angular radius of this ring, which is pretty easy. By the way, the ring isn't perfect because the galaxy that's being lensed in the background and the galaxy in the foreground are not both perfectly on axis and perfectly circularly symmetric, but you get the idea, it's going to work pretty closely. If we knew this radius and we knew the redshift of that lens and that source, which are obviously an elliptical and some very distorted spiral galaxy, then we would know the mass enclosed in this circle belonging to the lens. And that is not just the visible mass, that's the total mass, right? So we get an almost instantaneous measure of the amount of dark matter, or dark plus visible matter, enclosed within an Einstein ring. And as soon as, so Einstein predicted that these kind of effects should happen, and he predicted that in like 2020 or 2018, I can't remember, but no good examples of Einstein rings were discovered until the 1980s. And now we know of many hundreds. So that's a really good tool, all right? And just to get a feel of this, let's do another problem, okay, problem 3, where we're going to ask, what is the critical density if I have a gravitational lens that's at redshift 0.5 and a source behind it at redshift 1, okay? And just to help you out here, there's a really nice function in AstroPy called angular diameter distance that you can use that will solve the lambda CDM cosmology Friedmann equations and tell you those distances, all right? And then there's another one called angular diameter distance Z1, Z2 that you'll need if you want to get the distance from the lens to the source, okay? All right, so I'll scroll that down, or maybe I'll just leave it up so you can see how I did it if you want to look. And let's see if you can come up with a number there.
And once again,
Well, you need to copy and paste the line.
what?
Those are two different units, yeah. So
Okay, if you were able to get
Oh,
bend AstroPy to your will, and or just do this on your own. I got a number that you can see up on the left screen there, that it's the critical density is about 0.6 grams per centimeter squared, which is a surprisingly human scale quantity. In fact, when I first learned this, somebody said there's a rule of thumb that critical density is about 1 gram per square centimeter, because that's about the projected mass density of your thumb. If you hold it out, you're made mostly of water and your thumb is about 1 centimeter thick. So your thumb is about a gram per square centimeter. And it turns out that for a lot of galaxies, you know, or clusters of galaxies, their central density does get up to that level. It's kind of weird, right, to think that just your thumb has enough, the same projected mass as average an entire galaxy. But remember that there's a lot of space between the stars and the galaxy, right? And if you get about 3,000 stars per square parsec projected, you are capable of producing an Einstein ring, right? So Einstein rings are a case of strong lensing, you know, where you look at it and you say, wow, that's a gravitational lens, right? And that's what the official definition of strong lensing. After a short break, we'll talk about weak lensing, but strong lensing, gives this instant answer about the mass of some dark matter in some lens. And that's great, but only systems that get above the critical density can be measured that way. So that's going to restrict us to the central regions, to galaxies or halos, in other words, collapsed clusters. It's not going to be able to tell us about the mass, the dark matter distribution outside of the halos, right? And what that means is that less than 0.1% of all the lines of sight, all the directions you could look in the universe, are capable of strong lensing. The vast majority of what we see in the sky is not strongly lensed. So if we want to take a census somehow of dark matter, say, that's global and not just, or universal, not just confined to the halos, the centers of the halos, then we're going to have to come up with another way to use this lensing effect, all right? So we'll take maybe a pause here for 5 minutes to breathe or forget about AstroPi for a second, and then we'll talk about what weak lensing is, all right? Okay, so we have a lot of cases out there in the universe where we want to learn about dark matter, but we are not in the regime where we have Einstein rings or other very dramatic phenomena like being able to see the same object twice, multiple imaging, where you get two paths back to the same thing. That also requires reaching the critical density. Okay. But what if, so what if, for instance, we wanted to learn about the mass of that elliptical galaxy lens further away than the Einstein ring? Okay. Do we have any recourse? Well, yes. There are a couple of things you might think about doing. One is to say, well, what if I still know the bend angle? Anytime I know the bend angle, I can figure out the mass enclosed, right, by just using the deflection formula. And the problem is that, the bend angle is the difference between where you see it and where it really is, right? The problem is that we are not good enough at astronomy yet to take the elliptical galaxy and move it out of the way so that we can see what the unlensed position of the background galaxy is, right? So we are not able to actually measure the deflection angle. There is one case of gravitational lensing where the lens does you the favor of moving away from the background stars. Can anybody think of what that is? An eclipse, right? The sun. The sun moves across the stars, right? And so this is why gravitational lensing was first measured using the sun, is because we could take a before and after picture and measure the motion of the stars, okay? But once we're doing galaxies and stuff, that doesn't happen. Actually, it does happen for something called microlensing, but that's a different lecture. So if we're talking cosmological cases, we don't get to measure theta s, so that means we're in trouble. All right, so the lensing effect doesn't just change the position of the object, though. It also changes its shape, okay? So here, we're not going to talk about point sources anymore. Let's consider a case where we have a lens galaxy, and let's assume it's circularly symmetric mass distribution. And then let's say we had some circular source galaxy behind it, okay? Now, that galaxy is going to get lensed by this, maybe not enough to cause an Einstein ring, but we're going to observe it at some slightly larger radius than its source radius, its true radius, right? Because of the lensing effect. Now, because the mass is circularly symmetric, photons can only be deflected radially, right? There's nothing in this lens that can move photons around a circumference. And that means that the image of this galaxy will fill the same wedge as its source did, right? So it'll move from being here to being out here. And what that means is that its size and shape can change. So let's think about that. The major axis of this image galaxy here is, we'll call it A, right? Well, it's going to be equal to the angular size of the source galaxy, but it's going to be magnified by theta I over theta S because we're seeing it out here at theta I instead of theta S. All right, everybody see that? We can write that as theta I over theta I minus alpha, the apparent deflection times delta theta S. And then what about the minor axis? Okay, well, the near side of that galaxy, the nearer side has been deflected out to here. And then the farther side of the galaxy has been deflected out to here. So you might be able to see, and this is the equation for that, we could see that this delta theta S is going to correspond to a delta theta I given here, because we can just differentiate this formula, right? So B, the minor axis of the image, is delta theta I, and it's related to the original size of the circular lens in this way. Okay. So A and B, the major and minor axes of the image, are slightly different whenever there is a deflection like this from what the original source galaxy had. Right. Now, what we can do in this particular case is figure out what is the ellipticity of this image going to be. And there are different ways of defining ellipticity of an ellipse, but I'm going to use for the moment one where we just call it A minus B over A plus B, right? Which, as you can see, is 0 for a circle because A and B are the same, right? Well, if I take this A and this B and plug them in, I can see that my circular galaxy is gonna get turned into an ellipse that's given here by 1/2 of alpha over theta I minus d alpha d theta I. Okay. And this quantity here is called the shear of the lens. Shear because it takes a circular galaxy and will pull it into something with this ellipticity. And another thing that happens is that the galaxy could be larger than it started also. The area of this ellipse is pi times A times B, as opposed to pi theta S squared here for the original circle. And that gets larger by a factor that's equal, if you do some math, equal to alpha over theta I plus d alpha over d theta I. And this is called the magnification, because if the galaxy gets larger, the surface brightness is actually conserved by gravitational lensing, just like optical lenses do. And so if the galaxy image gets larger, it also gets brighter. Okay. All right, so what we see is that even if we don't have a dramatic change of the shape, we can get a slight one from a circle into an ellipse. So if I had a bunch of galaxies here, which I've labeled and colored, with letters here, and they're all circles, so that's like a background wallpaper. And then I plop a cluster, say a halo of dark matter right in front. What happens is that galaxy A, which is right along near the axis, gets turned into an Einstein ring or multiply imaged, right? And that's pretty dramatic. But the other guys out here, they are merely stretched. You can think of them as trying to turn into an Einstein ring, but not getting very far, right? So if we were to see this pattern of the background galaxies on the sky, I could measure that stretch amount, and I could also figure out the mass between them and the center of the cluster, all right? So this is what we call weak lensing. And I'll give a little spoiler here. There is one problem with using this method, which we'll talk more about probably tomorrow, but why doesn't this quite work this way? What makes this hard? And yeah.
You don't know the original size and shape.
That's right. Galaxies don't happen to be colored lettered circles, right? They have all kinds of shapes to start with, right? So if you see a galaxy that looks like this, right, on the sky, you are not generally impressed, right? Because lots of galaxies just look like that, right? So this is my definition of strong lensing and weak lensing, is that strong lensing, you know it when you see it, right? It doesn't look like a galaxy anymore. Whereas weak lensing makes a galaxy look like a slightly different galaxy, right? And so I have a picture of that, which is a few slides down, because we are doing okay, right? This is what's really going on. Well, we have colored lettered ellipses as galaxies instead of colored lettered circles. And so our image is going to look like that. We still, you know, if you look at A, you go, aha, gravitational lens. But if you look at these other ones, you're not really sure whether they're just funny, you know. And so how do we actually do this in practice? Well, what we'll find is, you know, the intrinsic shapes of galaxies are randomly oriented because the universe is isotropic and homogeneous, right? But these galaxies around here will have a statistical tendency to be more tangentially oriented than radially oriented because of the stretching effect, okay? So this is how weak gravitational lensing works, is we're looking for a coherence in the shapes of galaxies on the sky that would not be there in the absence of lensing. Now, lensing also magnifies objects, and it takes a galaxy and makes it look like a slightly brighter one, right? Well, again, it could have just been a slightly brighter galaxy to start with. We don't really know, right? Magnification works because if you see a collection of galaxies, you'll see that as a whole, they have a tendency to be brighter than the galaxies in some other part of the sky, right? But it's a harder measurement because shear is 0 in the absence of lensing. But magnification means you're looking for a change to a non-zero quantity. And an experimentalist in physics will tell you it's always easier to detect a change from 0 than to detect a change from some number to some other number, okay? All right, so that is the principle of weak gravitational lensing, is we're looking for a coherent change of shape, and that is defined by this quantity gamma, the shear. Okay. All right, so I'm gonna work out a formula. We have this thing here that says that the gamma is equal to alpha over theta I times d alpha over d theta I. Well, we also know what alpha is, right? For a circularly symmetric lens still, that it's equal to this stuff here. This is from an earlier slide. Enclosed mass, right, divided by the angle. And that means that we can form alpha over theta I, and that's just putting another theta on the bottom here. And that alpha over theta I turns out to be just the mean density within theta I divided by the critical density. And then we get this d theta over theta I. I can take the derivative of this equation, and it's all here. I won't go through it. Lots of things cancel out. And we find that d alpha d theta I can be written as the mean density within theta I plus 2 times the density at theta I. And this is true for a generic radial formula, all right? Generic mass distribution. So if I plug those two into these two things for the magnification and the shear, I find that at a given radius, I will see a shear which is equal to the mean sigma inside that radius divided by the sigma at that radius. Which we can also write, if we write sigma over sigma crit as kappa, what we find is that the magnification is equal to kappa along the line of sight, and the shear is always this combination, which is sometimes called delta sigma. I think you saw this on Gil Holder's slides, perhaps, was it yesterday or Monday? Okay, so here's where it comes from. And the remarkable thing is that these equations work even for non-circularly symmetric lenses. So any lens that you have, if you can measure the shear, the average tangent stretching in an annulus around that mass, all right, then that measurement is telling you something about the mass distribution of that lens, namely the mean mass inside the circle minus the mass density at the circle. And if you're smart enough to be able to measure the magnification of the galaxies in that ring, it's going to tell you the average mass density of the lens at that annulus, all right? So very nice, elegant mathematics that leads to this fairly simple thing. And all you have to be able to do is measure the shapes of the galaxies behind your lens. Okay. So let's see. Maybe I will talk for a little bit more, and we'll have well, let me go ahead and just do this problem, okay? Here's one I want to show algebraically. This goes with somewhat earlier material that an SIS and a point mass, that those Einstein rings enclose the same mass, and if they have the same radius, and that they're at sigma crit. I'm gonna leave that one aside for a moment. And then here's another problem. Let's take a graph of the tangential shear that's generated by a singular isothermal sphere galaxy. And let's make it the lens a cluster of galaxies with a sigma of 1200 kilometers per second. And the lens is at 0.5, and well, let's say it's that the sources behind it are at redshift 0.9. So the problem here is to go and make a graph of what the shear is versus radius from the center of that lens, okay? So I think since we only have about 5 minutes left before a break, maybe I'll just step through this problem instead of having you do it. Let me step through it. I think it'll help. So we remember this is the thing that we're looking for, right? This formula here for the tangent shear. And for an isothermal sphere, we got in a previous slide that the sigma is, the surface density is sigma squared over 2g times the impact parameter, which we could also write as DOL times theta, okay? And we also, in the previous question, we can integrate this from the center out to theta and find that the mass enclosed within theta divided by pi theta squared basically is sigma squared over g theta DOL. So we have this, the SIS is kind of cool because the sigma within theta is always twice as big as the sigma at theta. Right. So we get a very simple formula for the tangent shear of an SIS. This should be a capital sigma here, I realize, which it ends up being just that it's equal to the Einstein radius over 2 times the radius you're actually looking at, right? Or we can also write it this way. Right. So if I make a graph of that, I'll do that in AstroPy. First, I have to get my distances. And then here's a formula for the Einstein radius that we worked out before. And then I'm just going to take a bunch of thetas between twice and 200 times the Einstein radius. And I'm going to figure out that the gamma from them is just the Einstein radius over 2 theta. And then you can probably guess what the plot's going to look like on a log-log plot. It's just a straight line, right? Now, the Einstein radius is down here. The shear would become very large. In fact, it becomes infinite because we're stretching something basically into an entire ring, right? At the Einstein radius. But we're talking about weak lensing here. So don't use the weak lensing formula near the Einstein radius. But you can see we can go out like an arc minute. This would be 1,000 arc seconds, 1,200 arc seconds. Out here would be, say, 20 arc minutes. And the shear that's being applied to the galaxies in the background is a percent, okay? Or a fraction of a percent. So that means a circular object is just about 1% out of round once you get farther away, right? Let's see. Yeah. So that's how we could measure the masses of clusters out to larger radii than their Einstein radius. We have a whole bunch of faint background galaxies and we measure their shapes and we measure the average tangent shear in radii, in circles around that, then we can get back something about the mass of that galaxy, or what its mass profile is. Okay, so you will see here as a problem that I'm going to leave you with to waste your evening doing or something. And that is that I gave you a file that is a catalog of galaxy shapes, okay, measured by E1 and E2. And there's a few parts here, but I'll have you read that catalog, and it has 4 columns, the X and Y positions of the galaxies as a function, and then their shapes, E1 and E2, which I'll have to, actually, maybe you can't do this tonight because I have to define those for you. But when we do shear, we do things like this. So in this catalog that I gave you, I put a galaxy cluster in the center of this image. And each of these little whiskers here represents the shape of one galaxy. So the length of the whisker tells you how stretched it was. So a circular image of a galaxy would just look like a dot here. But the longer the whisker is, the more squashed that galaxy appears. And then the orientation of the whisker is showing you where the major axis is. Okay. So you'll see these whisker diagrams a lot. And I think I put 33,000 or 30,000 galaxies in here. Okay. All right. So you can look at that and say, that doesn't look too useful, right? It's just it looks like pickup sticks. Does anybody ever play that game still? I don't know. Just looks like somebody dropped a bunch of matches on the ground. But there's actually a ton of information in here, because if I take these galaxies and I average their shapes, okay, the part of their shape that comes from their own intrinsic shape averages to 0 if I do a vectorial average. But if all the galaxies in some vicinity are being lensed by this cluster, then we will, the intrinsic part will average down to 0, and we'll be left with a picture of just what the shear is. So if you do that and average the data in boxes, it ends up looking like this, okay? And now you can see this tangent pattern that grows weaker as we move out from the center of the cluster, right? And with this data, we have a constraint on what the mass distribution, including the dark matter of this cluster is. Right? All right, so that is the main idea of weak gravitational lensing. And we have some formulas that we can use at least for circularly symmetric lenses. And then tomorrow when I'm back, we'll talk a bit more about how this turns into cosmology. And then there's some, how do you assign an ellipticity to a galaxy that isn't an elliptical galaxy? It's an important thing, okay? Good.
Do you want to take some questions?
And yeah, I'm happy to do questions.
Yeah, let's do question. We have time. You actually finished a bit earlier.
Oh, right, I got 10 more minutes. I could talk more with that time. That's what I thought I would just.
Yeah,
Yeah,
no, that's perfect.
okay.
So you can call on questions.
Oh, okay. Well, right in front of me first is a question.
Hi, we have a question from Zoom. Are there any other conserved properties between the original and sheared/magnified image in weak gravitational lensing?
The thing that's conserved by gravitational lensing is surface brightness. Okay. And as we'll see in some later slides, there are constraints on what this distortion pattern can look like. It is, and just to, give it away, we will show that this gravitational deflection comes from a gravitational potential, which I think that you also got a formula for from Gil yesterday. And anything that comes from a potential ends up having some curl-free component. Now, these are not vectors. I'll show you later that these are spinors, or they have spin 2. These galaxy shapes are spin 2 quantity. But there's an analogy saying that you can't have something called a B mode in lensing.
So I wanted to ask, so I guess if you're very, very close to
galaxies that might be able to lens other galaxies, then you cannot see much, just because there's not enough stuff in between. So what redshifts can you probe with weak lensing in general? Or what redshifts are useful?
Right. It's a good point. So if we look at the formula for the critical density, which is here, it's easier to be a lens if the critical density is low, right? So first of all, we see there are two distances on the bottom and one on the top. So that means that it gets easier to be a lens as you get farther away from the observer, which makes sense, right? Because it takes less bending to make it around. Okay, so that's one thing. And another thing you can ask is, okay, let me put the source where I am and the lens where you are. Sorry, the observer where you are. And let's ask, what's the best place to put the lens if you want it to do more lensing for you? Well, in the limit where the universe is flat, so if we forget about general relativity for a second, DOL plus DLS equals DOS. And if you wanted to maximize this quantity, you would find that the best place would be halfway in between. Okay. So if we have a given source, we'll see later the equation for what's called the lensing kernel, which is how efficient is lensing along the line of sight. It peaks halfway, but it's halfway in some relativistic distance that isn't the same as half the Z or something, but it's pretty close. And by the way, this is true for any kind of lens, right? If I have a magnifying glass and I want to magnify something, I don't put the magnifying glass right next to my eye, and I don't put it right on top of the thing, right? The best place to magnify is halfway in between. Back in.
So far we've dealt with one lens. How would you deal with stacked lenses?
Yeah, so that is the next bit of slides, which we will do integrations along the line of sight coming up. And basically you just add up the deflections from each successive bit of mass that you encounter. Okay. Let's see.
I have noticed for the magnification formula, if you plug in a SIS here, you would get the magnification always greater than 0. So does that imply that the energy is not conserved or anything?
That's a good point. So this magnification formula for the circularly symmetric lens, which is, let's see, this one, the kappa one here, right? Okay, so it's a little tricky. This is a subtle question. It took me a long time to figure this out. Does everybody, if I take that mass and put it there, does it mean everybody in the universe sees this galaxy brighter? Right. So you're a source of light. I'm an observer, right? I see you at some brightness, and then we put mass here. Okay. Well, that somebody. I'll see a lot of magnification, but as you point out, that formula suggests that nobody in the room would see a dimming. So that doesn't seem right, because now everybody's getting more photons than they used to, and energy is supposed to be conserved. Okay, so the subtlety is that if I take mass out of the rest of the universe to put it into this mass here, I'm changing the background geometry a little bit so that everybody else far away will have a slightly larger angular diameter distance. So basically, if I gather mass into a blob, I'm getting magnified, but we are stealing photons a little bit from the people who are not near the line of sight. Yeah. Well, in other words, to make a galaxy cluster, I had to make voids somewhere, and voids have a negative kappa actually. Yeah.
So is it possible that all galaxies in our observable universe have some distortion due to weak lensing?
Yes, yeah. Our view of the universe is not the right one. It's not the truth. Of course, the galaxies that are close to us have a hard time getting lensed by anything. So they are not distorted to any significant amount. But our distant universe is, you have to take lensing into account for almost anything you measure. In fact, there are numerous times in the literature where somebody claimed to have found some super bright quasar or galaxy or something like that. And after they put it on archive, somebody had to say, that's probably just a lens normal galaxy. Yeah.
Could you have in clusters where the shapes of the galaxies are correlated without any lens?
Yes. So he's just brought up one of our weak lensing nightmares, which is that galaxies are not randomly oriented. Okay. Galaxies know something about their neighbors. In particular, like you say, in a cluster, they might have a tendency to want to line up towards the center of the cluster or something like that. So when this is one of the biggest uncertainties, actually. It's called intrinsic alignments, or IA. And it's if you just walk around a lensing meeting and say IA, you'll see people shudder, because it's a false signal, right? Now, if we knew the redshift of every galaxy, we'd be somewhat better off, because if you're the observer and then there's a lens here, and then there's two sources that are here and one of them's here, they look next to each other on the sky, right? But they're really very far away from each other along the line of sight. And so they're not going to know anything about each other's shape. So those two things will be uncorrelated. You can assume that. So there are different kinds of intrinsic alignment effects that we do definitely have to worry about. Fortunately, they're smaller than the lensing alignments for distant galaxies. But since we are now at the state of the art is to be trying to measure the lensing effect to a few % accuracy of the lensing effect. And at that level, we really do have to worry about how aligned galaxies are with themselves. Yeah. Any more? There's one. Okay.
You mentioned magnification means that we're stealing brightness from not along the line of sight. So do we ever use voids to try to constrain like the lensing potential perpendicular to the line of sight, or is that just way too complicated of a signal to even go for?
Well, lensing intrinsically integrates things along the line of sight. So it's, if you want to make a 3D map of the universe's mass, like of voids and things, galaxy redshift surveys are better because we can measure the redshifts and resolve distance with Hubble's law, right? Weak lensing surveys are really only like 2.5 dimensional. We can do something called tomography, which is to look at galaxies at different redshifts, right? Because a galaxy where you are is going to be lensed by everything between you and me, but a galaxy where this gentleman is will only have seen the mass between he and me, right? And so you're going to have different lensing, and algebraically I can try to separate the mass on the line of sight. But it's hard for us to do anything that's highly resolved on the line of sight. That said, people have measured the mass density or lack of density in voids using gravitational lensing. We can see that the places that have no galaxies also have no dark matter. So that's a semi-answer to your question, I think. Yeah. One more.
So you mentioned like through lensing we can be able to compute the mass of the dark matter. So in our Milky Way, like the satellite galaxy, if we see the lens through lensing, can we able to compute the subhalo mass also?
People have gone through a lot of effort to try to tell if we could see subhalos from some lensing effect. And with weak lensing, it's very difficult because we need a lot of galaxies behind something to see the weak lensing effect, even for a regular galaxy. We can't, first of all, our galaxy's substructure is too close to us to be an effective lens. All right. People have tried to use gravitational lensing to look for subhalos statistically, but that is more often done in the context of strong lensing, because what strong lensing will do, what a subhalo will do, if you have an arc like, oh, keep going the wrong way. Okay. if we look at an arc like this one, if there is a subhalo along the line of sight here, it can put a little kink in this arc, okay? Or make it lumpier than it would be otherwise. So, and there's also something called microlensing or millilensing that can occur. So we can generally only find subhalos as some small perturbation to some strong lensing. Yeah. Yeah.
Wonder if it's a good time to take a break. Thank you,
Yeah.
Gary. Thank you so much.
Okay, I'll see you all tomorrow. We want this.